Hi, and welcome back to Integrated Science. So still we're talking about our wave behaviors and how different types of energy can be moved through a system. And so I want to show you just kind of what we talked about previously. Just the ideas that waves are repeating disturbances and that they can travel through a medium, a solid, liquid, or gas, or they do not have to travel through a medium, such as our electromagnetic spectrum waves. We have two different types of mechanical waves, which are transverse and longitudinal. And then once again, our electromagnetic waves that do not need a system to travel through or a medium to travel through. Nope, that's not going to work. Hi, and welcome back to Integrated Science. I'm Miss Sparks. So previously we have been talking about our wave behavior. So started here, and we went through just what are the different aspects of a wave that we can look at qualitatively. So we talked about a wave being a repeating disturbance and that it needs a medium to travel through, a solid, liquid, or gas. And I'm also going to throw in plasma there. We have two different types of waves that we're going to talk about, mechanical and our electromagnetic. And mechanical waves need a medium to travel through, while electromagnetic do not. Our mechanical waves can be broken down into two different types of waves in which we can measure the wave front. And those two different types of waves are transverse and longitudinal. And so we're going to go through and kind of talk about the properties of the waves. So once again, we have introduced already crest and trough is the peak and valley of a transverse wave. And then the compression and the rarefaction are the energy motions for a longitudinal wave. And then we went through and we talked about amplitude being the energy in which the wave is carrying with it. So the higher the amplitude, the more energy. So let's kind of talk about what that looks like. So first off, we have wavelength, which is just the distance from a point on a wave to the identical point on the next wave. And this is going to give us a whole bunch of pieces of information to kind of solve with. So we're really looking at quantitative pieces of information today. How can we solve for these different types of variables? So once again, the first one is wavelength. I feel like it's always easiest to measure from crest to crest. You could do trough to trough either, but it has to be the identical point on each. So the distance from any point on a wave to the identical point on the next wave. And we can solve that mathematically by taking the wave speed and dividing by the frequency. The next portion that is really helpful in quantifying how a wave behaves is its period, which is the amount of time it takes for one motion through a cycle or one oscillation. So the definition for a period is of a wave in physics, the time that it takes to complete a cycle or wave oscillation to occur, meaning that it goes through one crest and one trough and back to this line right here, which is called the resting point. So the resting point would be like if there was no energy moving through the system, and then you cause a disruption and it causes the energy to move through. So one period is through one crest and one trough and back down to the rest point. How we measure a period is by taking the time it takes and using the frequency to help with that. So the wave period is the time it takes to complete one cycle, once again, from rest point up to crest, down to trough, and then back to rest point. So that's one period right here. The standard unit for a wave is in seconds and is inversely proportional to the frequency of the wave. So our equation that we use to find period is, we use a capital T for it, equals 1 second divided by frequency. The higher the frequency of the wave, the lower the wave period, meaning the faster it's moving, the lower the period that it's going to go through that cycle really, really, really quick. So what is frequency, you might ask? Frequency is the number of wavelengths that pass a given point. So if it's a high frequency wave, it should be moving through really quickly. I always think of like a Richter scale, if you've ever watched a sci-fi movie where the Richter scale is going off the charts because of an earthquake and it's moving really, really, really fast. That's a high frequency. Whereas if it's going really, really slow, it's a low frequency. So frequency of a wave is the number of wavelengths that pass a fixed point each second. And we refer to this once again as frequency. Our equation to find frequency equals wavelength and velocity. And we're going to take our velocity and divide it by our wavelength, which is represented with this symbol right here, which is a Greek symbol for gamma. So let's try one. So if we take a look here, the question's asking, the illustration below shows 3 boats floating on the water, moving up and down, perpendicular. These are our longitudinal or transverse waves, sorry. And we can see that the wave is traveling to the right with a velocity of 3 meters per second. What is its frequency? So we have our distance. We have our 3 meters. And we also have how many meters there are apart from it. So we've got 3 meters per second, which gives us our velocity. And then we have our distance at 4 meters. And so once again, if we take a look with frequency, we are taking our wavelength and our velocity and dividing it by wavelength. Our velocity is 3 and dividing it by the length. So we should get 0.5 or 0.75 is our frequency of the wave. And we measure that in hertz. Frequency is measured in hertz. Wave speed. We've already know how to find speed. Speed equals distance divided by time. Well, this is kind of the same concept. It's just that we're using different terms. Our distance is wavelength divided by time, how fast it's moving per second. So wave speed is the speed at which a wave travels. Wave speed is related to wavelength, frequency, period, and by the equation, wavelength equals frequency times wavelength. And so once again, it's the same idea that we've used these terms before. We're just now applying it to something slightly different. A few more terms that we want to make sure that we understand are reflection, diffraction, and refraction. And so this is a way in which waves can, when they interact with another wave or a different type of medium, they can disperse their energy. So the first one is a reflection. So kind of looking in a mirror, it's the bouncing back of a wave when it meets the surface. So when you look in a mirror, the light is bouncing back and going into your eye, and you see a reflection of yourself. Diffraction is the bending of a wave around an edge. So think about, like, if you've ever heard maybe like a firework going off far off in the distance, is that it's probably the energy has bent around different objects to get to your eardrum. And refraction is the bending of a wave when it passes between 2 substances in which the speed changes. So I like to think of this as like a light or energy going through a different medium. So if you've ever looked into water and saw a fish or a rock or a shell, and then you went down to grab it and it wasn't exactly where you thought it was, that is refraction, meaning that it's bending the light just ever so slightly to cause it almost to look like an illusion that it's not in the same spot. And so when we talk about wave interference, we can talk about constructive and destructive different types of interferences, and constructive is just increasing the amplitude and destructive is decreasing the amplitude. So if we want to push more energy through a system, we call that constructive. We're building it, kind of construction, and destructive is we're taking it down, we're destroying it, bringing it back down. So constructive is more energy that we are going to force through a system, and destructive is taking away the energy and bringing it back down a few notches. So we're going to spend a lot of time talking about frequency and how that looks with different types of waves. And so as we move forward, we're going to start talking about the Doppler effect and how that energy is applied to many different things. So hopefully this was helpful. Thanks.